All right, ladies and gentlemen, welcome back. We're looking at the second part of the biomolecules. Last day was just talking just intro chemistry type stuff. This is going to be the basis for almost a huge chunk of the year, talking about water, acids, bases, and buffers. Okay, so first of all, the things that you need to know, don't forget you have your template, so start jotting these ones down and pause it if you need to. It's just that what water is. So let me just get a pen up here. See how that's doing for color. Water is the most abundant molecule in our body. So everything's made up of water. Humans are about 70% water. And so that's why it's so important. And water's got some really interesting properties that we're going to talk about in a minute that makes it so interesting, or makes it so important. So first of all, just a little recap from Chemistry 11 for those people that didn't take it. Pay close attention here. We have a concept that's called polarity, or polar. When things are polar, it means opposite. In chemistry, it means that we have unequal sharing of electrons. So when we have something like sodium and chlorine, sodium tends to have a positive charge, positive one, and chlorine was a negative. That's why they were attracted together. But that whole molecule is neutral, right? One plus and one minus. Even though the whole thing is neutral, it has a tendency to have more of a positive charge over here and a negative charge over here, because that sodium gave an electron to that chlorine to make that bond. We call this a polar molecule because of that unequal sharing of electrons that leads to partial charges. Okay, so partially charged is better to say. Okay, the reason why we're going over this polarity is it has a lot to do with the water molecule. All right, so more specifically, when we're talking about the water molecule and the polar charging, we're talking about the hydrogen bond. So what this is, it's a weak bond, so it's a weak attraction between the hydrogen on one molecule and a negative charged atom on another molecule. So let's look at water, for example. Okay, so here we have a water molecule. It has a sharing of electrons between the hydrogens and the oxygens. If we come close to another hydrogen water molecule, there's going to be a slight attraction between these two. Let's try green. Between these two molecules, because if you look at the charges, oxygen is a 2 minus charge, hydrogens reach plus. So what happened is it bonded to these two hydrogens, leaving these ones with a partial positive charge. And all this little thing here means is partial. And this one was a partial negative charge. Same thing, these were partial positive, and these were partial negative. So when we have positives and negatives together, there's going to be an attraction between them. So what happens here is there's going to be an attraction between those positives and the negatives on opposite molecules. So we just draw a hydrogen bond like this. Okay, so it's that charge or that attraction between them. Okay, so take your time, stop this, write this down, draw the picture so you can have a visual of what this looks like tomorrow when we go over it. So the reason why I go over that hydrogen bonding is it lends itself to all of the properties that water have. It's really important molecule in our body for lots of reasons, and this is what allows it. So first of all, water is liquid at room temperature. Why is that important? If it's at room temperature, it was frozen, or it was a gas, we wouldn't be able to have it going through our veins and being able to transport all the different things that it does. Okay, so it needs to be a liquid in our bodies for transport. Right, so example, right, the blood, all the different dissolved molecules are dissolved in water, which is liquid. Okay, so that's one. Second thing, it's a universal solvent. A solvent means it dissolves things. And what I mean by things is things called solutes. So I'll put that in. Okay, so it's universal solvent. So when things are, for example, like sodium chloride, this is a polar molecule. And if you have something like water, oops, let's erase that. because of these partial charges, it has a tendency to want to be attracted. So if you look at this partial positive charge here and the partial negative charge of chlorine, it has an attraction. So what it ends up doing is it starts pulling this way. And if you look at about another water molecule, oops, apparently they're different colors. This negative end of the oxygen and the positive of the chlorine is going to pull as well. So what ends up happening is it pulls this sodium and chlorine right apart, and it's left with just a sodium ion and a chlorine ion dissolved in water. So that's what allows salt to dissolve in water, is the pulling by the water due to this hydrogen bond. Oh, sorry, not hydrogen bond, due to the polarity. Okay, next thing. Water is cohesive. So this water cohesiveness, why is this important? First of all, if you don't know what cohesive means, it means sticky together. So in other words, water is sticky. And why is this important, or why do you know this? Well, if you put a piece of paper on top of water, and we'll show you a little demo in class tomorrow, it's going to stick if you put it upside down. Same thing if you see the little water minnows, and they look exactly like this. Hello. What happens is when they're sitting on top of the water, the surface tension is strong enough to support them due to the stickiness between the molecules. So why is the water sticky? It's due to these hydrogen bonds. Due to this attraction between them, it just has that extra little hold together. So in terms of living things, why is this important? Just look at a tree, first of all. In order to get this water way down from the roots into the top of the tree, what happens is it uses its stickiness. So when leaves open, what happens is water starts leaving, it evaporates, and when water leaves, other water molecules below it they're sticky together, and so when this water is leaving, the other water gets pulled up. So it's called cohesive property of water, and it allows this water to go from way down in the roots all the way up to the trees. Why is this important in terms of us? So we'll say, one, trees. And the second thing, why for us? It's in our blood as well. When blood starts flowing through vessels, if only one molecule went, all the rest would just be left behind, but when our blood gets pumped, it's attached to other water molecules behind it, and it pulls it along. Okay, so you can think about blood transport. I hope this pen color is okay. It could be terrible, so just give me some feedback tomorrow if it is. It looks good on my screen, but you never know. Okay, temperature buffer. So water, as we know, when you put a pot on a kettle, it takes a while for it to warm up, and that's a good thing, because if we go outside where it's 40 degrees sometimes in the summer, and our body's at 37 degrees, it won't do very well for us to go up to 40 degrees Celsius inside our body. Okay? So what happens is that water doesn't heat up as fast, which is great. The other thing, if it heated up really fast as well, if it was evaporating, that would not do very well for our bodies. Okay? So a temperature buffer, same thing. If you're at -2 outside, what happens when things are below freezing? Well, it's going to freeze solid, and if our blood did that, that would be a problem as well. Okay, so it prevents, overheating or freezing. I think that probably is a terrible color. Changing. Let's go back to old reliable blue. Okay, so let's just finish off here with acids and bases. I'm not sure. I think we might be running out of time here. So we'll go over this really quickly. Oops. So acids, as you guys probably know from before, and bases are just opposite ends of the spectrum. If we have something that's an acid, it's a pH that is less than 7. And bases are pH that is greater than 7. And what is it if pH is equal to 7? That is neutral. Things like water. Okay. Other things about acids. Acids are compounds that have H's in front of it. which we call a hydrogen ion, and bases end in OH. Okay, so let's say end with OH and starts with H. So an example would be hydrochloric acid. And we tend to write AQ after, it just means dissolved in water. And bases, sodium hydroxide, ends in OH. Okay? And the other thing is just know that the pH is on a log scale, which means it goes up by times 10. So if you have a pH of 2 and a pH of 3, the difference between 2 and 3 is actually 10 times. So if you were a difference between pH 2 and pH 4, you're going up 2 divisions. Each one is times 10, so that would be a times 100 difference. Okay, finishing off with buffers. This is something we're going to see a ton in the circulatory system, so we're not going to do a whole bunch. What a buffer does is the same thing as water did with temperature. This is a pH buffer, which means whatever you put into it, so for example, carbonic acid, this prevents the pH from getting too low which means acidic, or too high, which means basic. Why is this important? Well, here's just one importance. Enzymes need to be at a specific pH in order to function. If the pH goes too low, the enzymes won't work. Okay, so it's pH specific, and you'll see this in digestion unit next. Okay, so we'll go over these buffers again in class, but that's just a quick little intro, so hopefully that helps. And if you have any questions, be sure to write them down. Have a super night.